All right, welcome to our pre-lab video for lab E19, Electrochemistry. Good news, this is the last pre-lab video of the semester and the last pre-lab video of the course. In fact, this is the last lab of the course. There are only skill builders and the final exam from here. So let's talk a little bit about what electrochemistry is. That'll go a long way to explaining what we're doing in this lab and how we're doing it. So electrochemistry is kind of the natural thermodynamic offshoot of redox reactions. So if you think about the lab that we did last week, the virtual lab, we did a bunch of redox reactions where we were looking at how reactive one substance is versus another. Now, this all comes down to thermodynamics because each of those chemical reactions that we look at were either spontaneous or non-spontaneous. They either happened or they didn't. Now, for redox reactions, instead of thinking about things in terms of heat energy, it's often useful to think about things in terms of electrical energy, because after all, it is the electrons that are moving, and the movement of electrons is known better as electricity. So when it comes to something called a voltaic cell, also known as a galvanic cell, also known as an electrochemical cell, what we're talking about is a specific way that we can harness the movement of electrons through a series of wires, through a circuit, to do electrical work. Another way we can refer to this is simply as a battery. And so here's an example of a voltaic cell, an electrochemical cell that we have set up through a pair of beakers that are separated from each other. In a battery, we see the same kind of thing happening, only everything is kind of condensed into one container that has some partitions in it. The parts of the voltaic cell are as follows. There is a cathode. The cathode is the part of the cell where we see reduction taking place. There's also an anode. The anode is the part of the cell where oxidation takes place. Easiest way to keep those straight is that cathode and reduction both start with consonants, and anode and oxidation both start with vowels. Now, the cathode and the anode are connected to each other in two different ways. First of all, there are wires. The wires help to connect the cathode and the anode to each other, and also control the flow of electrons. And so in this case, we've got a zinc and copper cell. We can see that the electrons are flowing from the zinc through the wiring to the copper. That makes this part the anode because the electrons are flowing out of it. The zinc is being oxidized in the process. And that makes the copper cell the cathode because the electrons are flowing into the copper, and copper 2+ is turning into copper metal as a result. Now, on its own, this process would only last for maybe a couple of seconds, microseconds, not very long at all. And that is because the cells would eventually become polarized. If I did not do anything, I would end up having a whole bunch of electrical charge here and a whole bunch of positive charge over here as those electrons moved from one side to the other. Polarization is bad. Because basically it makes it so that it is difficult for the next migration of electrons to occur. So to combat this, we use something called a salt bridge. A salt bridge allows the ions to migrate by basically replacing what was lost. So on the anode side, where we had lots of negative charge leaving, the salt bridge ultimately adds nitrate ions. And so nitrate ions come in and they help to replace the electrons that were lost. And so I've got a whole bunch of positive charge over here that is now being matched by negative charge to keep it from becoming polarized. And on this side, I've got a lot of copper 2+ that's turning into copper. So this side's getting more and more negative. Sodium ions come in and replace the copper ions to keep the charge consistency the same inside of that copper cell. So all 4 components are necessary. You can't have oxidation without reduction. You can't have a cathode without an anode. The electrons don't actually travel unless there are wires to help the electrons flow from one side to the other. And if there isn't a salt bridge to help neutralize and diffuse the charge, then the cells end up becoming polarized anyway, and they're eventually become useless. Now, we can ultimately describe just how much energy is given off by a voltaic cell by measuring something called the electromotive force. The electromotive force, the cell potential, tells us how much we're supposed to get. And ultimately, when we put that to use, we're going to be able to measure that in the form of voltage, cell voltage. When these experiments are done under standard conditions include 1 molar concentrations for the cells, as well as 298 Kelvin temperatures and 1 bar pressures. When those conditions are met, these are called standard cell potentials or standard electromotive force. And we give that as cell voltage, EMF is given just as E. Standard EMF is given here as E0. So E with the degree symbol on it. We can calculate these standard EMFs using something called a reduction potential. The reduction potential is measured against something called the standard hydrogen electrode. So the standard hydrogen electrode is this chemical reaction where hydrogen ions are turned into hydrogen gas by the addition of 2 electrons. By definition, the reduction potential for the standard hydrogen electrode is 0 volts. So this is our standard in which we base everything else. Which means that every single voltage value, every single E reduction potential that we get is based on how it reacts to the hydrogen electrode here. So when the substance forces the hydrogen to become oxidized and flips this around, we know that it has a greater reduction potential than the hydrogen. We're going to measure a positive voltage in that case. When the hydrogen acts as the cathode and the other substance acts as the anode, we know that it's going to have a lower reduction potential, and that value will end up coming out as negative because the electrons are flowing from the hydrogen, or excuse me, from this other cell to the hydrogen. Now, by convention, all of our EMFs are written as reduction potentials. And so what we end up getting is a table of standard reduction potentials. And they tell us how much energy, how much voltage would be applied when that particular cell is acting as the cathode. If it's positive, that means that it's a good thing. That means that it is going to give us positive voltage, which we can use to do work. If it is negative, that is a bad thing. That means that it is not going to act as a cathode very often. Good chances are that it's going to act as an anode, and we're actually going to see the oxidation take place for it. If we wanted to look at oxidation processes, by the way, all that we would have to do is flip the equation and flip the sign to get the oxidation potential as opposed to the reduction potential. Now, where we can find this data is in reference tables. And there's a really good reference table in Appendix 6 in your textbook. Appendix 6 in your textbook looks at reduction half reactions for a number of different kinds of substances. So if I click on that, it's going to take me to your ebook. And here we have our list of standard reduction potentials. And if we look closely at this list, the things that we kind of expect to be at the top are at the top. For example, fluorine is the most electronegative element, which means that it is the most likely to want to grab electrons. And what do you know? It's at the top of our reduction potential list. If we go further down, we can see some other kind of cool things. So here's chlorine here. Here's oxygen acting as an oxidizer. Here's silver ion acting as a reducer, or being reduced rather, acting as an oxidizer. Here's copper 1. Here is the transition between copper 2+ ion and copper 0 ion, or I'm sorry, copper 1 ion. Here's the reduction potential for tin. Now notice right here in the middle, here's our standard hydrogen electrode, 2 electrons. And now we start getting into the stuff that would rather not be reduced, that would much rather be oxidized. Very common example, tin, or excuse me, lead. Lead. You know, here look at an example. We've got zinc. Zinc is reacting as a oxidizing agent here and becoming reduced. Very negative value, negative 0.762. Not so great. Which is why zinc metal, if I flip this around, zinc metal turning into zinc ion would have a standard oxidation potential of positive 0.762 volts. If I flip the equation around, I also flip the sign of the potential. So as an oxidized substance, as a reducing agent, zinc is a great reducing agent. Its ion is a terrible oxidizing agent, which is why, again, we don't see too many reactions with zinc ions. We see lots with zinc metal, not so much with zinc ions. So what good is this information? What can we do with it? Well, as I said, as we were looking through the tables, the more positive the value of the reduction potential, the more likely it would be to be reduced. The best oxidizing agents out there have large positive reduction potentials. The more negative it is, the more likely it is that we're going to find that oxidation. And the best the best reducing agents have large negative reduction potentials. We saw zinc as that example there. Zinc ion, terrible oxidizer. Zinc metal, zinc with no charge, great reducing agent. Now, one important note, even though we've been talking a little bit about thermodynamics here, and even though we've seen some similarities between reduction potential equations and how kind we treated things for Hess's law, understand that reduction potential is an intensive property. Now, if you don't remember what an intensive property is from Chem 105, an intensive property is one that is related to the substance itself, not the quantity of the substance. So from that angle then, unlike Hess's law, where we had something that was definitely extensive, if I double the amount of sodium, I'm going to double the output of the reaction, not only in terms of the amount of product, but also the amount of energy that that product kicks out. This is different. This is an intensive property, so the stoichiometric coefficients are not going to affect things. If I end up needing to double a reaction to make sure that I have enough electrons to get it to balance out, that's not going to affect its reduction potential. I'm not going to have to end up doubling the reduction potential as a result. The only thing that they have in common is if I flip the reaction, I flip the sign. Same as what we did before with Hess's law. Other than that, we treat it completely different. Now, in terms of taking Ecell and determining the total electromotive force, the total voltage of a voltaic cell, there are two things that we can do. We can either look at the reduction potentials themselves, identify the cathode, identify the anode, and subtract the reduction potential of the anode from the reduction potential of the cathode. That's this first equation right here. And when you're using a table of values, that usually makes sense. It's kind of easy to go with. Now, if you are combining reactions, I've got my reduction, I've got my oxidation, I've determined the oxidation potential and the reduction potential. I can take those two values and just add them together very similarly to what I did in thermodynamics with Hess's law. Again, minus that multiplication thing, and get the same answer and the same result. These two equations are just two different ways of doing the exact same thing. Keep in mind something though. For an electrochemical reaction, our electromotive force, our Ecell, has to be positive if the reaction is going to be spontaneous. Again, we're in a thermodynamic zone here. We're either going to talk about reactions that are happening and are spontaneous, or reactions that are not happening and are not spontaneous. The only time we consider anything about equilibrium is when the battery is dead, basically. When there's no voltage going through it at all, that's when we talk about equilibrium, because at that point, delta G is equal to 0, and we see an equilibrium between the two reacting systems. This is going to follow a lot more like what we saw with the thermodynamics. It's going to be spontaneous in one direction, non-spontaneous in the other direction. Let's do a couple of examples. So first of all, let's determine the Ecell value for these two chemical reactions. And for that, we're going to have to go back to the tables that we were looking at just a minute ago. So the first one, hydrogen reacting with fluorine to make hydrogen ion and fluoride ion. Now, right away, if I follow my oxidation numbers here, I can see that I went from 0 to +1 for the hydrogen. The fluorine went from 0 to -1. So my hydrogen was oxidized. My fluorine was reduced. I need to keep that in mind so that I find the right half reactions to use. So for hydrogen, well, that one's easy. The half reaction that I'm interested in is the standard hydrogen electrode. That's got 0 volts. The other reaction that we're interested in, fluorine and 2 electrons to make 2 fluorides. That one I need to go back to the tables and look up. And that one's going to be high on the list because fluorine is extremely electronegative. 2.866 volts. So since I've identified the oxidation and the reduction, then Ecell is equal to the reduction potential for the cathode, which would be what was reduced, and minus the reduction potential for the oxidation. So 2.866 volts minus 0 volts would give me 2.866 volts. So that's how much voltage we should expect from this hydrogen fluorine voltaic cell. Now let's look at this next one, nickel and cerium-4. All right, so here we are. Cerium-4 to cerium-3 gives us a reduction potential of 1.720 volts. So coming back to here, we can see, first of all, we can see the cerium has gone from the +4 state to the +3 state. So this is the reduction, which means that this is the cathode. Nickel has gone from a 0 state to a +2 state. So this has been oxidized, which means that this is the anode. As we saw on the previous state, cerium-4 with an electron going to cerium-3 has a value of 1.72. Nickel +2 going to nickel 0. We found that value before. We'll find it here again. -0.257. So to find the cell potential, I take the cathode, 1.720 volts, minus the anode, -0.257 volts, 1.72 minus -0.257 gives me 1.977 volts. So that's how to solve these using just using the reduction tables. If that method really doesn't work for you, what I can show you is just one quick little trick that can help that out for you. It's really pretty easy. Basically, if I want it to match, if I'm trying to figure out how to make it match, I can see that the cerium reaction matches. I got cerium-4 going to cerium-3. The fact that I don't have 2s there actually doesn't bother me all that much because, again, just because I double this doesn't mean I do anything to that. But if I want to look at it from the standpoint of the nickel, nickel going to nickel +2 and 2 electrons, the oxidation potential for this would be +0.257 volts. And if I add those two equations together, kind of similar to Hess's law, what I'll see is that my 2 electrons cancel out. I end up with exactly the same formula as what I started with above. To find the cell potential, I would just add those two together. And so I end up with the same 1.977 volts. So either way that works for you, go ahead and use it. If it makes sense for you, if you can kind of follow the logic of I'll just pull the data from the reduction potentials and I'll just make sure that I can identify the cathode and identify the anode, great, go for it. If you need to draw it out like this and see how I ended up at the final answer and do it that way, that works too. Either way is perfectly fine and acceptable. Now, let's go ahead and turn to the pre-lab to go ahead and see how this applies. Question number 1. A voltaic cell is constructed using a chromium electrode immersed in a solution of chromium 3+, chromium 3 chloride, and a nickel solution immersed in nickel 2 chloride. Write the overall cell reaction and calculate the standard voltage reading. Okay, easy stuff. This is basically, you look at the cell potentials, you're looking at the reaction that existing between chromium 3 and chromium metal versus nickel 2+ the nickel. Now, you are going to have to get this all balanced out from a charge standpoint. So do be advised that 3 and 2 are not the same number, and you are going to have to adjust the coefficients to get the electrons in versus the electrons out to match. But you would use the table of values here to figure out what the cell voltage is and what the anode and the cathode are. For numbers 2 and 3, you're told that you're putting a metal of some sort in hydrochloric acid. Describe what you would observe. Well, for that, you're going to need to look at the reduction potential table again. So in this one, I'm looking at a strip of nickel versus hydrogen. What I want to do is I want to compare the two. So I've got nickel here in pink. I've got hydrogen here in yellow. Which one of these two is more likely to grab those electrons? The hydrogen ion in the acid or the nickel 2 ion, which we don't have? Well, the answer here is the hydrogen ion. It's got a higher, more positive reduction potential. So this reaction is going to be favored. This reaction is not. What's going to be favored instead is the reverse reaction where the nickel turns into nickel 2+. And that's just so happens to be what we're trying to do, because we're not putting nickel 2+ in there. We're putting nickel metal in there. So since hydrogen ion is a stronger oxidizer than nickel ion, the hydrogen ion will oxidize the nickel metal. And so from that standpoint, this is a chemical reaction that would take place. You just need to describe what you would see when that chemical reaction does take place. For number 3, same kind of idea, just look at mercury versus hydrogen ion. Number 4, what would happen if you remove a salt bridge? Well, I described that earlier at the beginning of this video. If you didn't catch the answer to that, go ahead and rewind it, go and find out why the salt bridge is there and what would happen if there was no salt bridge. Would copper metal be able to reduce iron 3 to iron 2? Same kind of question as 2 and 3. You're looking at the reaction between copper metal versus iron 3 to iron 2. So iron 3 to iron 2 is up here. Let's put that one in blue. And Copper ion is here in green. Which one is the more likely one to be reduced? Does the reduction that fits match the reduction that we're asking you to do? Yes or no? Explain it. So that's all for this particular video. When you get to lab, I will give you a better explanation in terms of the details for what we are doing that particular day and just how what kinds of things that you can expect to do. I'm going to do a pretty cool demonstration as well, and we'll kind of walk our way through that one when it comes. But until then, I will see you next time in lab. Have a great day.